Welcome to nCast, the podcast from NOps. Each week, we'll explore the world of cloud cost management, the latest in AWS optimization, and getting practical about your FinOps journey. Join us as we dive deep into the latest trends, tools, and best practices, while having conversations with leaders and luminaries who are innovating on the front lines. Our goal is to provide value to the community through insights and practical advice that will help you to achieve your FinOps goals. So whether you're in engineering, leadership, finance, or a cloud professional, this is the place for you. Sit back, relax, and get ready to join the conversation on nCast.
Hi, everybody, and thanks for joining us for another episode of nCast. I'm very excited about today's guest, and I think it's a real opportunity to have a conversation with somebody who's doing research in the area of cloud optimization and efficiency. So today we have Haoran Qiu from the University of Illinois Urbana-Champaign, who recently graduated with his PhD. Haoran, give us an introduction and tell us a little bit about the research that you've been doing over at Illinois.
Thank you, James. Thank you so much for inviting me here. It's very exciting. Hello, everyone. This is Haoran Chu. And as James mentioned, I recently graduated from University of Illinois with a PhD degree. And my research thesis topic is on cloud resource management with efficient and online learning using machine learning-based approaches. And it's always excited for me to talk to industry people about how academia thinks about autoscaling and other resource management in the cloud. And this is also a hot topic in the academia. So I'm really excited today to share some recent research from academia on these topics.
We're very excited to have you. So what caught my attention was some published work and presentations that I saw swirling around with your name on them in the area of multidimensional autoscaling. I think it's really a subject area where we're coming to the confluence of a lot of different traditional approaches, and we're thinking about different ways to disrupt the way that we traditionally do autoscaling. So just to provide a little bit of history, why don't you tell us about where we've been with autoscaling and what direction we see autoscaling, either at the container level, but maybe even at the node level. What direction are we headed?
Yeah, that's a great question. It's always good to look back in the history to see what people have been doing in this area. I think, to me, autoscaling is a very classic problem. It started from the beginning of cloud computing, where we just have this idea of cloud. And at that time, the computing paradigm is not, Kubernetes, not serverless, but people know a lot about stream processing, like batching, those kind of jobs. And MapReduce is at that time a really hot topic because we just have the idea of big data analytics, and then MapReduce is a very popular computing paradigm to help people to do this kind of data processing, data analysis. And at that time, autoscaling is already kind of like a rising because people are doing autoscaling for the number of virtual machines, the number of replicas, and the number of nodes at that time, because people haven't come to the container level. And then I think with the rise of web services, people are building their own either monolith or microservices, building their web services in their own startup companies. A lot of enterprise companies are also shifting their in-house application to web services, microservices. And then that, helps the rise of Kubernetes, I believe, because people run their applications on containers a lot. And they need, such a container orchestration platform, such as Kubernetes. And then autoscaling is getting even more popular because when we have so many containers, we're not only adjusting the number of replicas, number of nodes, we are adjusting the, number of containers. And for each container, how should we decide the size of the container? And that, brings the topic or the method we're calling them like multidimensional autoscaling, we are resizing the container, we are also deciding the number of containers for the application. So I think that's how it goes. And the people learn a lot. They have a lot of approaches in the traditional days of managing the applications, and they also bring such heuristics or learned algorithms from that period to the Kubernetes. And this is also still like ongoing, still like evolving, and it's also like a growing research area as well.
Right. And so I remember in the days when we were first adopting container orchestration platforms, what Kubernetes brought to us, well, what Docker brought to us was consistency in deployment and configuration. And then
exactly.
Orchestration brought to us the ability to manage many containers at scale. And still at this point, it felt like that the ability to adjust at a service level and also ensure high availability, reproducibility, disaster recovery. But we were still scaling our Kubernetes clusters by hand. If you needed to add an additional node, then literally went and added a node into the cluster by hand, and it was a capacity planning exercise. But Cluster Autoscaler obviously is one of those tools that really changed the game. There tends to be a general conception out there. We all know about tool sets like Vertical Pod Autoscaler and Cluster Autoscaler and Horizontal Pod Autoscaler, right? So these are three tools out there that allow us to scale both our containers and nodes. But at the same time, people tend to find that there's an inherent conflict between horizontal pod autoscaling, we'll start there, and vertical pod autoscaling. So what new concepts does multidimensional autoscaling introduce, and how does it address the inherent challenges that people face every day?
Yeah, that's another great question. To me, like when we say the word autoscalers, there's always like a confusion. I remember last time I went to KubeCon, and then I talked to people using the word just autoscalers. And then I assume they understand what I mean is like vertical autoscalers or horizontal autoscalers, or those you can simplify them as like a workload autoscalers. But then the person I was talking to like assume I was talking about like the capacity resizing is kind of like autoscaler, like the cluster autoscalers. And then we talked for a long time, and then we realized that we are talking about different autoscalers. So I think definitely we should be really careful about these terms. As you mentioned, there's like vertical autoscalers, horizontal autoscalers, and the cluster autoscalers. And I think multidimensional autoscalers as a new concept kind of like combines vertical autoscalers and horizontal autoscalers. But the difference is, so first, let's look at horizontal autoscalers and vertical autoscalers. Horizontal autoscalers refers to the process of dynamically determining, how many containers should you maintain at any time for your application deployment in Kubernetes, for example. And the vertical autoscaler refers to like for each container, for each replica in your application deployment, what should be the so-called the size of the container in Kubernetes. That refers to the CPU limit and the memory limit. CPU limit just is the number of vCPUs or the number of MIDI cores, and the memory limit is simply the how many megabyte or gigabyte of the memory capacity you assign to your container. And like people know, there's like a well-known phenomena that vertical scalers and horizontal scalers cannot be simply concurrently used on the same metric for your assigned applications. And a simple example is, let's say there's like a load increase, and your horizontal autoscalers decides to add another replica, and then now you have two containers instead of one. But then the incoming loads to each container may be smaller than the situation where you only have one container. because your load, although it's growing, but then it's split into two containers. And then the VPA comes in to say, now I have smaller loads, so I don't need that, much capacity. So I shrink the container. And then the horizontal autoscaler reacts to this by adding another container because the load is still increasing. You cannot just shrink the capacity. And then with the, adding another container, VPA kicks in to say, oh, the capacity should be shrink again. And then the end of this, ultimately I'll have like a lot of small containers, small tiny containers. But maybe the optimal solution should be I'll just have maybe 3 or 5 large containers to handle this load. Yeah. So I think this is the dilemma of the using like vertical autoscaler and horizontal autoscaler as two independent agent or controllers in the system. But multidimensional autoscaler or MPA, like multidimensional pod autoscalers, it resolves this conflicts by combining the two decision making. And we have like a heuristic based approach on how to combine this kind of like two decisions when facing the same system state or workload state using some simple rules. For example, for compute intensive application facing what kind of load, how should we favor one decision first, and then like maybe vertical first and then horizontal, or like horizontal first and vertical, to avoid ending up in the dilemma. And like in my research group, we also work on some machine learning based approaches. Like I have the state input from the application level, performance metrics, or system level, for example, resource utilizations or the system metrics, and then I use this as input, and then I train a machine learning agent to compute some prediction or decision. This is like a combined decision, whether it's either vertical scaling or horizontal scaling, or it can be both. So it kind of like resolve this conflict. And that's the major difference. Like MPA is not like independent vertical autoscaler plus horizontal scaler, but it's like a organic, like a single one decision agent.
Right. And this conversation leads me to so many different thoughts. There's so many factors that actually go into efficiency. Over at nOps, we've been doing a lot of work into quantifying what excess capacity means in a cluster. And sometimes heuristic-based approaches do not serve us well. If we follow, that there's an open cost standard that does a standard distribution that the memory costs, X percentage of your overall hourly charges, and compute, and then cost so much, and then GPU overweighs both of them. But when you get into the details, it's really dependent on the type of instance family, whether it's memory optimized, whether it's compute optimized, the type of workload, whether you prioritize memory intensive applications or CPU intensive applications. And so the calculus may be that with one type of workload, we want to prioritize memory as the dominant efficiency metric because that's what I'm paying for, versus GPU as the dominant efficiency metric because that's what I'm paying for. So given all of those factors in my perspective, I'm wondering, what do you think about sort of the dangers associated with an overly simplistic heuristic approach? It feels like the logic tree would have to be pretty robust, versus what are the limitations or capabilities of ML based approaches?
Yeah. So I think I work on this for a long time actually. Like at the beginning, I work on like building distributed systems, like building heuristics. At that time, I didn't work on like machine learning based approaches, because I believe we people are smart. After playing with the applications and the system, we can come up with some simple rules or simple heuristic, and in this way, it's good enough, and then we can achieve optimal performance efficiency. But then I think the at that time the time I began to switch to machine learning is in the cloud computing era, or like data center, applications are heterogeneous. And as you said, they are like compute intensive applications, memory intensive applications, or some other like network IO kind of like applications. They're so different from each other. And the other observation I have is application workloads are dynamic. They're not like static, like assuming like a constant arrival rate and doing the same thing all the time. They have their like load spikes, like fluctuations. They're dynamic. And the reason I think rule-based approaches or heuristics can be improved is it comes with so much engineering effort. And at that time, I was doing I think performance engineering, like figure out how should we allocate the resources minimally, don't over-provision resources to achieve the application service level objective. And this is a great task, for performance engineer to figure out. Spend some time profiling the application, get them data, and do some simple analytics, and then figure out, what should be the threshold to set in the VPA or HPA. And I think that's great for like a static application, for a single application. But then when you want to scale this approach up to like maybe thousands of applications that can change from time to time, you need to, spend a lot of human effort on this. And not to mention that every time you provide application, whenever there's some workload changes, dynamic, conditions, you need to reprofile the application again, like reanalyze the data and then come up with like a new parameter. Those parameters need to be tuned from time to time. And then after you test the parameters, you deploy the new rule or heuristics into the production system. And what machine learning brings here is we can automate this process. And heuristic-based approach are simple to implement, and they're great, they're robust. People understand them very well. But then the problem is like how can we dynamically adapt to new application? And that's exactly what machine learning can provide us. Like machine learning-based approaches are data-driven. And the reason why we can use machine learning in cloud platforms is we have abundant data. Like we have monitoring infrastructure already built in almost every data center. We have also great open source tools to, get application traces like Jaeger, or get those monitoring data from Prometheus. And those are very convenient. And while running those applications for a long time, we already, have, got this data for a long time. But machine learning is the tool to extract, those parameters from this data. And an example is like we have such a work called Firm. It's a resource management framework using machine learning for cloud microservices. And what we are doing is simply to treat the application data from the Jaeger traces, like application, the performance, the latency, throughput, available rate, load patterns, this kind of data. And also with the container level system metrics like utilizations, cache hit, or cache miss rate, those kind of system metrics. We combine them together and then go through the neural networks. And then it gives us the two dimensional of the autoscaling decision. Like, should we do a vertical autoscaling or should we do like horizontal autoscaling as the action? And then we have the feedback mechanism. It's like a loop, because after we execute these actions from the machine learning agent, we can get the performance from the application as the feedback, whether the latency goes back to normal within the SLO level, or it's like even worse, this kind of feedback. We also get a feedback from the resource utilization. Does the utilization, increase or decrease even under utilization, or is it good enough? That means a lot, because we don't want to over-provision on this kind of resources. And I think with this, machine learning framework, it's kind of like automating the process. And that's the main difference from my perspective, comparing, traditional rule-based approaches versus machine learning, how machine learning can augment this kind of approaches.
One of the interesting things that we've been looking at in terms of cloud efficiency and cluster efficiency is how to quantify excess capacity. And let me give you an example or two. Our compute copilot engine, for instance, we'll from time to time make a decision to over provision a node into a Kubernetes cluster. And an example might be that my workload might only require an extra large instance type, but on the spot market right now, 2XL may have a very steep discount and a much higher stability rating. And therefore, it makes more sense to add more capacity, which makes it very interesting. If that node is underutilized, but it's sitting idle, meaning it's not sustainable, it's not being used by anyone else, and at the same time, it's at a much lower price to get excess resources. Is that excess capacity waste, or have I truly saved money? And so it kind of leads me to a future where I think that there's more feedback between horizontal and vertical pod autoscaling and node provisioners like cluster autoscaler or Carpenter, which particularly we want to make the most efficient decision in terms of packing a node, but maybe I've made a decision that would impact how many pods that I want to schedule, because it would be more effective to schedule more pods on a cheaper capacity option or a more sustainable capacity option versus smaller number of pods on a smaller node size. What do you think about that? It feels like the future becomes more and more complex.
Yeah, that's a great example, I would say. I think currently, at least in academia, people tends to think about those systems, one by one, like those kind of like I would say like controllers or agent one by one. Like for example, there are like a lot of work on autoscalers, like rule-based approaches, model-based approaches, machine learning-based approaches, and then they build a lot of system models to better autoscale the workload, either the vertical autoscaling or horizontal autoscaling. And their objective or optimization goal is to improve the resource utilization at the container level as much as possible, because they only focus on the workload they're managing. And on the other hand, there's a lot of papers or work focus on like I would say like similar to Carpenter, do the capacity, the cluster level capacity planning, capacity management, resizing the container, like whether we should include a new node into the Kubernetes cluster or not, or what kind of node should we include. And their goal is is different from the workload level goal. Their goal is to do like a better job in bin packing to achieve like as high utilization at the cluster level as possible. Or they touch a bit on the sustainability concept. They want to save the cost, save the energy, as much as possible. And your example is a great one for us to think about how can we combine the two together. And I think another agent here plays another important role is the job scheduler in the scheduler in Kubernetes, for example. It kind of like bridges the two. Like for example, when you have a new node from Carpenter included to the existing cluster, and should I schedule the job onto the pod onto the new node, or should I migrate the old ones to the new node and then schedule the new job onto the old node? So that's to me it seems like a bridge between the Carpenter and the autoscaler for the workload. And so far in academic, I haven't seen such a solution that combines in a holistic manner, combine the solution from workload autoscaling and cluster autoscaling together, and to achieve the same the same goal. I think the ultimate goal for any cloud provider is to reduce the cost to remain the cluster level utilization as much as possible without violating the workload level metrics. For example, the container utilization goal specified by the users, or the application performance goal specified by the users. So I think, towards the future, there might be efforts, or or now like there already been some efforts from industry that I'm not aware of. But I think having a holistic approach to optimize for the ultimate goal is needed to command the two.
Right. Well, we've started to delve into the ML based approaches. Why don't we dig a little deeper into ML based autoscalers and talk about the promise. The promise is that they will make intelligent decisions. I think that in our own research and our own approaches to both container right sizing and spot efficiency and all of the things that we do in our own engineering and R&D, that the ML, you have to strike a balance between how we can use large groups of data to improve heuristic based approaches and find novel new ways to tune, and using ML to make real time decisions, because in both cases the proof is in the outcomes. How efficient do both performance do both solutions perform? So maybe you can tell us a little bit more about how far and how effective and what some of the considerations are with the ML based approaches that you've been working with.
Sure. Yeah. So for machine learning based approaches, I think we can talk about first maybe we talked about the motivation for using machine learning previously, just briefly. And I think in the middle, there's another category of approaches. That is, I would say it's not called machine learning, but it's called model-based approach. Their motivation is also to automate the process of, how can we replace the heuristics by some models. But to me, they're different from machine learning-based approaches in this manner. Like they're model-based approach, and they're I think we can call them white box-based approaches. And machine learning-based approaches, we can call them black box-based approaches. By black box, I mean most machine learning-based approaches, they use neural networks to approximate something, right? And in the model-based approaches, what people are doing is we build some Q networks, for example, using Q theory or layered Q networks. And then by doing those like Q networks modeling, we can simplify the whole system, the real system, into like a model, like a network of Q. And of course, we need to make some assumptions like about what Q type it should be, like a general Q or some other type of Qs. And we should, have some assumptions about the system. And most of the times, those assumptions are simplified. They can be inaccurate. And then people need to, again, like provide some data and then provide application to build such a model. And after they have this model, then they sort of automate, the decision making by building such like a controller into the Kubernetes cluster and make decision, right? So I think you have seen such work, of course, in industry. Those are coming from the control theory. This is, I think, 1 or 2 years before machine learning really kicks in. I think machine learning-based approaches is similar to this kind of approach. Is we also model the whole process as a control feedback loop. And I was mentioning briefly, we have the states, the measurements from the system, including application level metrics and the container level system metrics. And we also have the neural network as the so-called policy or agent. Like once we have this kind of system state measurements, I go through my neural network to generate some output. So those measurements are input, and then the decisions or the predictions are the output. And then this output goes back to the Kubernetes to be executed, like how we should auto-scale the number of containers or how we resize the containers, things like that. And then we obtain the feedback, which is how the utilization look like, how does the application performance look like. And then this is like a one iteration. It goes again and again. It forms like a feedback loop. And the difference is in machine learning, we rely on a black box, although it looks like unexplainable now. But let's assume we use like a neural network as a black box. and this black box takes the input and generates the output. And the reason we use this is, I think for one reason, we replace the system model by this neural network. And the good thing is we don't rely on any inaccurate system assumptions. And instead, we are learning from the data, learning from the feedback from the system. After we have the state, we have the decision, the output, and how good the output is. And this concept is well studied in reinforcement learning, an online learning approach, online learning algorithm. And we can show that, theoretically, these approaches can converge. And the other reason that, machine learning-based approaches is better than model-based approach is we can incorporate any metric into the system very easily. And as an example, some people want to make their autoscalers to be performance aware. And that means like our autoscalers can react to the application metric, any application metric. For example, the processing rate, the throughput, the latency. And this can be easily added to the reinforcement learning model by using this metric as the reward signal, or including this metrics in the state vector as the input to the neural network. But this cannot be easily added to the model-based approach because you need to rethink about your model. Where should I use this metric plug into the string theory, or where should I insert this variable to it? And that's one reason. And another reason is, once I have this machine learning model, I can easily train to optimize for my end objective. For example, I just want to improve the utilization of the containers. I just want to meet the application as a load. I just train to meet this either in the loss function or the reward function, and it's a simple optimization process. It's just this simple. So I think that's the two main reasons why machine learning-based approaches can also work easily in these scenarios. So that's simply the introduction to the machine learning-based approaches. And I think another part of your question is also super valuable. That is, now we know the capacity of the machine learning-based approaches, but how should we how can we understand why it's better than heuristic-based approaches, and under what scenarios does it work all the time, or are there any like robustness or reliability concerns? I think that's the valuable decision we should make while we are transitioning to production, because in academia we work on like building prototypes, like system prototypes, or like some approaches. Theoretically, we prove it works, and then we show it in some prototype it works, but we never test it in a very large scale production system. So I think that that's also one lesson I learned from visiting IBM in 2022, because at that time, like we worked with IBM to try to operationalize one of our machine learning based approaches for multidimensional autoscaling, and then we do this operationalization in their in-house cluster to test on their like some applications, some data processing applications. I think the lesson I learned from that experience is they're keen on like automating their autoscaling process, and they have like a whole bunch of applications deployed in their system. They have those kind of like workload fluctuations, but then they deploy simple rule-based approaches, which are very conservative because a lot of times they are doing like over provisioning, and that wastes a lot of resources, resulting in like low utilization.
Well, and that's the number one complaint about rule-based approaches, is that they're oftentimes, they work, but they're not very effective in terms of overall efficiency gain.
Right, exactly. And then like because those applications are like high-stake applications, so they don't want to just do some testing, do some aggressive autoscaling to put the application into risk. And that's the reason they're really keen on like try to see if machine learning based approaches can kick in. And then my lesson learned from this experience is although they they hate rule based approaches, they hate like conservative heuristics, but at the same time they're also very conservative in trying machine learning. And the reason is machine learning based approaches has a training stage and has a like a online serving stage.
Right.
Because in the training stage, you need to train your learned model, your like randomly initialized model. Like you need to go through this trial and error stage. Let it try. It's like a newborn, like a baby, into the
Well,
world.
and I'll cut to the chase. We don't have the ability to do trial and error in production environments, right?
Yeah, exactly. Like any error or anything goes wrong in production can be problematic, and that's the one of the main reasons like stopping us from like adopting machine learning based approaches. And we have workaround actually. Like usually we have those testing clusters, or we can build simulators to train your machine learning model using some collected data from the real production system.
The real production, right? Yep.
Yeah, those are workaround. And in this way, we can use like transfer learning. We don't start from the randomly initialized model, but we start from like a trained model from like a simulator or testing cluster. So that seems to work well.
Well, and we use this approach a lot in our spot automation, also in our commitment automation, because we do have a lot of data, which allows us to replay simulation and make different decisions. Now, I think the outcomes are not always perfect, but at least we can learn a lot from these. So what does an approach like that prove to you? Does it improve initial results or make the ramp up of ML based approaches less painful?
So I think using this approach, we have a solution called like a bootstrapper for like machine learning based approaches. It's like with for the MPA in Kubernetes, we first use the VPA and HPA as the navigator in the cluster to collect some data, and then we train the machine learning based approaches on this collected data, and the learning algorithm guarantees that the learned model is at least better than the baseline.
As good as what's in production today.
Sorry, what?
And said it's at least as good as what you're running in production today. Or are those the results that you saw?
Yeah. It's like at least as good as the baselines you are using, like the data source you're learning from, which is the the standard VPA and HPA. And that's already good, starting point. You go through this bootstrapping process, and then you put your half-trained machine learning model into the production, let it run for a few more episodes, and then interacting with the true system, and then you ramp up like much more quickly compared to you start from the randomly initialized model. And I think that's one of the challenges we went through.
Well, it's really interesting stuff. And one thing I could tell you is that I think that we could talk all day. But unfortunately we don't have all the time in the world today. So I really hope that we can get together for a continuation of this conversation, because I think people out there are going to be really interested in, and I, for one, am very excited to be a part of what's going on from the industry side of things, to really push the frontiers with the new thinking around all of the various autoscalers, whether we're talking about horizontal, vertical, node autoscalers, and really the feedback loops between them, and then all of the outside influences, because we could talk for days about suitability and making geo-shaping workloads or clustering workloads to specific availability zones. There are many decisions that we can make that are based on factors that are even outside of the cluster. And especially when it comes to commitments, to pricing plans, reserved instances, there's a lot of things going on. And so needless to say, it's a fascinating topic. But for today, I'd love for you to leave us with, in 1 year, in 3 years, things are happening faster. What do you think that the near term future is for autoscaling?
Yeah, I think it's always hard to predict for the future, but I think personally speaking, I think the future for autoscalers is one thing is we should definitely have like a multi-dimensional autoscaler, ready for use in production. Like so far, we don't have like a very robust approach. Even like the rule-based approach, it's not yet ready. And I think this should be maybe the first thing happen maybe in the next 1 or 2 years, and resolving the conflict between the independent VPA and HPA. And I think the second trend I was seeing happening is we might have like a hybrid approach that combines rule-based approaches and machine learning. It's like we don't use machine learning to like such a black box to do like the decision making from end to end, but instead we use machine learning to augment or assist the existing heuristic approaches, maybe to replace one of the variables or to make some predictions that can be used in some rule-based approaches, or it can simply try to automate part of the process coming into play in the rule-based approach pipeline. So I think in this way, we kind of like eliminate the robustness challenge or the training challenge in the machine learning based approaches, because those training can happen offline, not like completely online, hurting your system. And on the other hand, we are trying to also eliminate the human effort, like building into the rule based approaches. So that might be like a win-win, might be like easier to transition to production system. And this hybrid approach is kind of something I'm also really interested in, like the interaction between human and machine learning. So this might be the two trends I hope to see at least coming into 2 years.
Haoran, I couldn't agree with you more. I think that we're there is a transitional period, if you will, where we're going to see a larger blend, and we have to pick some place to start, but ultimately we see where the future is taking us. Well, I really want to tell you how much I appreciate you joining us here today. I'd love to have you on again, and I know there's a lot more that we can and hopefully will talk about. But for today, I just want to thank everybody who's out there and listened for the entire episode. As I often say, if you stayed this long, you're probably as big a nerd as we are about these topics. And so we hope that you tune in next time for other interesting opportunities to talk to thought leaders in the area of cloud optimization. Thank you very much, Haoran.
Thank you, Dan.
Thanks for tuning in to nCast. We hope you enjoyed the episode. As you can tell, we love to geek out on all things cloud optimization. If you have any questions or feedback, we'd love to hear from you. You can find us on LinkedIn, Twitter, or Instagram, or just shoot us an email at ncast@nops.io. If you'd like to learn more about the continuing innovation over at nOps, or about our free FinOps platform where you never pay anything unless you save money, check us out over at www.nops.io. Until next time.